Discuss some trigonometry application problems. I'm going to look at 3 through 6 here. It's talking about harmonic motion. It says, consider the following situation. A mass oscillating up and down while attached to the bottom of a spring can be modeled using simple harmonic motion. If the weight is displaced from its equilibrium position a maximum of 7 centimeters and it takes 3 seconds to complete one cycle, answer the following questions. Well, let's kind of think about this a second. Here we have this spring, and at the bottom we have some kind of a mass, and whatever that is, it doesn't matter. And here it is at its resting position, okay? Well, it's saying up here that if the weight is displaced from its equilibrium position, where it's at right now is kind of balanced out, we're going a maximum of 7 centimeters. That means when it's stretched all the way out, and here's the weight down here now, it's been kind of stretched out further to where now it's down to like that. And I probably could have drew that next to it or something. That would have made a little bit better sense. So here's my initial thing here. So here's the spring resting. And then if it's going to be pulled down, it kind of looks like this. And so what this is saying is that if the weight is displaced by a maximum of 7 centimeters and it takes 3 seconds to complete one cycle, that means 3 seconds to go all the way down and come back up. Here's what we've got to do. Let's look at these questions. What is the amplitude of the modeling function? Well, that's going to be 7. Okay? The amplitude is going to be the maximum displacement right there. Okay? Number 4, what is the period of the function? The period is going to be 3 seconds. That is going to be the time that it takes to go through one cycle. 3 seconds, okay? One cycle. Those are pretty easy. Amplitude is going to be the displacement, that maximum displacement, and the period is going to be how long does it take to complete one cycle. Number 5 says, what's the frequency? Well, by definition of frequency, according to our curriculum, the frequency is equal to 1 over the period. And so that is going to be 1/3. So the frequency is going to be 1/3. Number 6 says, write a possible equation of modeling this. Well, we had a couple of possible equations that we were given in our curriculum, and those are d of t, or the distance as a function of time, is equal to a times the cosine of omega t, or d of t is equal to a times sine omega t. And so basically I could pick either one of these to work with. If we remember that A is my amplitude right there, and that we have a formula given to us that tells us that. Let me create myself a little bit of space here. The period is equal to 2 pi over omega, and we know that our period is 3. So I substitute 3 in for period. 3 equals 2 pi over omega. See, what I'm doing is this. I can use either the cosine or the sine function to model here, but I have to know what A is, and I have to know what omega is in order to be able to write this equation. Likewise here, A or omega. And so I need to solve for this, okay? So what I'm going to do, I'm going to make this as easy as possible. I'm going to put this over 1, and I'm going to do cross multiplication and division. So it's going to be 1 times 2 pi, which is 2 pi, is equal to 3 times omega divided by 3, and I've got omega. It's 2 pi thirds, or 2/3 pi. And so I can just use either one of these. So I've got one possible is d of t is equal to a, which is 7, my amplitude, times the cosine of omega is 2 pi thirds, or 2/3 pi, t. And that's one way of modeling it.